Hello everyone, welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the Cape Chemistry Unit 1 Paper 2 from June 2023. We will be working through a Module 1 question from the area of energetics, which focuses specifically on the topics of Hess's law and Born-Haber cycles. So let's get into it, okay? So this is question 1D, and part 1 is asking us to state Hess's law. Now, Hess's law states that the total enthalpy change for a chemical reaction is independent of the route by which the reaction proceeds, okay? So there are multiple ways by which a reaction can proceed, and whichever route it takes, the total enthalpy change will end up being the same. And so we will work through that in a little bit more detail later on into the question, okay? So that was D part 1, okay? So part 2 is now asking us to construct a Born-Haber cycle for the formation of lead-2 fluoride, PbF2 solid, showing clearly, using equations, the steps of the enthalpy changes involved. Okay? So what exactly is a Born-Haber cycle? A Born-Haber cycle is just an enthalpy cycle, right? And it includes a wide variety of enthalpy changes like a lattice enthalpy, enthalpy of formation, atomization, ionization. So it involves a wide variety of enthalpy changes. And so we have to make sure that we capture that. But before we even get into constructing the Born-Haber cycle, because we're going to do it for the formation of lead-2 fluoride, let's look at the possible routes, right, that we could use to form lead fluoride, because that will be an integral part of what we're showing ultimately in the Born-Haber cycle. So let's just I'm going to write an equation here to show there are two possible big routes that we could take to forming lead-2 fluoride. So let me just write that here, so we are all on the same page in that respect, okay? So we can start from, if we're making lead-2 fluoride, right, fundamentally at the basic level is comprised of lead solid, so Pb solid, right, and F2 gas, right? So that's a fluorine gas, okay? At its most basic level, these are the elements in their normal state, normal physical states that we're going to combine to then form PbF2. And so I can show an arrow going from here to show that we can combine these two elements in their normal physical state to form PbF2 solid, right? And whenever we go from the elements in their normal physical state, the element to the compound, right, the solid compound here, we call that a delta H of formation, right? So that's the enthalpy of formation. The standard enthalpy of formation can be denoted as delta HF. So that's one possible route that we could take to form lead-2 fluoride, right? The other route involves several steps. So here is one of those steps. So I'm just going to write several steps here, right? So again, we are starting from the solid lead and the gaseous fluorine. And we're going to go through several steps. Those steps are going to include an atomization step, right? There's going to be an ionization step, right? Ionization step. And there's also going to be an electron affinity step, right? So there are several steps there that we have to go through, right? And once we go through those steps, what we will end up with, so after we've gone through atomization, ionization, and electron affinity, what we're going to do is we're going to end up with gaseous forms of these, okay? And so what we would end up with, the gaseous ions is what we would end up with here. And so those would be Pb 2 plus in the gas phase, right? As well as 2 fluoride ions that would be in the gas phase, right? And when we put these two together, these two ions together, the coming together of these gas phase ions to give us, right, ultimately the lead-2 fluoride, we're going to call that delta H lat. So that's our lattice enthalpy, okay? And so what you will realize here is that there are two ways. There are two possible routes that we could take to making PBF2. The first one is where we would just do the enthalpy of formation, right? And then the second route is that we're going to go from these elements in their normal state. We're going to go through all these steps and then finally put these gaseous ions together to form a PBF2, okay? So overall then, we could say that if we take our arrow, so imagine that we imagine the cycle going in a clockwise direction, right? And we start here, right? And we're going this direction. We're going around, right? If I were to do this several steps, let me call this several step. Let me call it delta H I theta, so the several steps. What that would mean then is if I were to go in a clockwise direction and I say delta Hi theta, so I'm taking this direction as positive, and I say delta Hi theta plus delta H theta lat, this one is going against, this arrow is going against my clockwise arrow. So I'd say minus delta HF theta is equal to 0 because I've just made a complete circle. Okay, so these two are going in the same direction, my delta Hi theta and my delta H lat. So I keep those as positive. And then the delta HF theta is going against it, so I make that negative. And they all, I've completed a cycle when I do that. And so it all has to add up to 0. So what this means is that ultimately, if I wanted to find my lattice enthalpy, my delta H theta lat, right, it would be equal to, so all I'm going to do is bring both of these over the other side of the equal sign. So then it will end up that delta H theta lat is going to be equal to my delta H of formation minus, because I'm going to bring it over, minus the enthalpy change for all those several steps that we spoke about taking place right here. Okay? So this is an equation that we can come back to later on. So let's just box this equation for now. Okay? So remember now that this question was asking us to construct a Born-Haber cycle, and the Born-Haber cycle is going to be made up of all of these individual steps, the lattice step, as well as the formation step. Okay? Now, it's important to note before we even do the Born-Haber cycle that the enthalpy of formation, because we're putting two elements together from their normal state to form a new compound. It's an exothermic process. So delta H of formations are generally negative, right, in their sign. When we do a lattice and lattice enthalpy as well, we are putting two ions together and forming a new, right, 1 mole of an ionic compound. So this is also going to be an exothermic process, right? And within here, there are different signs that we will need to account for, and we'll talk about that once we're putting up the Born-Haber cycle. But it's important to note from the jump that these are going to be negative in their sign, right? And so we have to reflect that on our Born-Haber cycle as well, okay? Because you do remember that the Born-Haber cycle is an energy level diagram. So let's bring up the Born-Haber cycle now that we can construct for the formation of lead-2 fluoride. So here it is. Right? Here we are. Okay, here we are. Let me just move this preliminary work a little bit over to the left so we can have a very clear view of the pitch dome. Okay, all right, so here we are now. Perfect. All right, so here's our Born-Haber cycle. So the two key features that I want to point out to you immediately is that because our delta H theta of formation, right? Because that is negative, we show the arrow going down. So again, we're starting with the elements, the lead in the solid phase and the fluoride in the gas phase, and we're going to form PbF2 solid. So that's our delta H theta of formation, and that's exothermic, so we show the arrow pointing down. The lattice energy, as we said, is when we're putting the Pb2 plus in the gas phase together with the 2 moles of the F minus in the gas phase. When we put those two together and form the PbF2 solid, that's our lattice enthalpy. And that's also exothermic, as we said. And so we show that arrow pointing down. Okay? So now we have to capture the several steps part that we spoke about. Okay? So as presently constructed, the two parts that I've spoken through, we've gone from the element in their normal state to the PbF2, and then we've gone from the gaseous ions to the PbF2 solid. Okay? So these are the in-between steps that we have to capture now, which correspond to this portion here. All right. So if we have Pb solid, right, what we want to do first is we want to atomize that. And atomization means that we're forming a mole of gaseous atoms. So we're gonna say that, okay, there's gonna be a delta H of atomization that's related to the lead solid becoming lead gas, because we have to atomize it, we have to break those bonds apart to get those atoms free and in the gas phase. And so that's an endothermic process. So we show that arrow pointing upwards because it's an endothermic process. It's going to require energy to break the solid lead apart to become now lead gas. Okay? And we have to do a similar thing for the F2 gas. So we see that there are 2 fluorine atoms. So we're going to have to do that 2 times. So we say we're going to do 2 times the enthalpy of atomization of F2. And if again, it's an atomization step, so it's going to be positive. And so we show the arrow going up, right? And so now what do we have? We have atomized the lead. So now we have lead gas and we have the fluorine atoms in the gas phase. What else do we have to do now? We have to ionize our gaseous lead. So that means that we're going to take off an electron off of it. So that's our first ionization. So that's an enthalpy of first ionization. So we take off an electron off of it. And so we end up with Pb plus E minus. Okay? And of course, we still have our 2 F atoms in the gas phase from before. We're going to have to also do a second ionization of the lead, the Pb plus. So we're going to take off again another electron from it, thus forming Pb2 plus in the gas phase. And we're going to write the electron beside it as well. And we still have our 2 F atoms in the gas phase. Okay? No. So far, we formed the Pb2 plus gas ion, which we need in order to form the PbF2. So we're good on this part. Now we have to focus on the fluorine atom, right? So we have this fluorine atom in the gas phase, but we want to get to F minus eventually. And so what we're going to do is we're going to put an electron on it. And so it's going to become then negatively charged. And it's going to become F minus, and there are 2 of them, so we have to account for that as well. Okay? And so because there are 2 of them, it will be 2 times whatever the enthalpy of electron affinity for an F atom is. Okay? And so now we saw that the ionizations were endothermic, right? The first ionization and the second ionization, because we have to put in energy to take off the electron. So these are endothermic, so we show the arrows going up. But the first electron affinity, we were putting on an electron to the fluorine atom, is an exothermic process. So now you see our arrows are coming back down. Okay? And so with that, that is the entire Born-Haber cycle. Okay? So we've captured everything that we need here. We have our formation step, our lattice energy step, and then the in-between steps to get our gaseous ions, okay? And so now, let us move on to see what else is being asked of us. But if you showed all of this, right, and you showed the correct arrow, the arrow pointing in the correct direction, then you would have gotten all 6 marks, okay? Okay, so let's move on to see what else is being asked of us. So let's move on over here now. Okay, so let me just clear everything from here. And really, all I really want to leave is this little formula down here. Okay, so I'm gonna clear all of the preliminary work that we did in order to come up with the Born-Haber cycle. So let's just clear all of this for now and just leave that overall equation that we're gonna need to use at some point. Okay? All right, so here we go. Bam, bam. Just clear all of this. All right, so we're good to go now. Okay, so we're on to part 2 now, part 3 rather, and part 3 says table 1 shows the enthalpy changes associated with the Born-Haber cycle, right? Using the data in table 1, they want us to calculate the lattice energy of PBF2. So essentially what they're asking us to find is delta H lat, which we know is going to be equal to the delta H of formation minus all of these several steps that we spoken about earlier in the Born-Haber cycle. Okay, so let me just clear these off. So this is the table. They're showing us the enthalpy of atomization of lead, first ionization enthalpy, second ionization enthalpy, the enthalpy of atomization of the fluorine, the formation of PBF2, right? And then the first electron affinity of F. So we have all of these values here, and we have the associated signs with them, right? Remember, we had said that the enthalpy of formation would be negative in sign. The first affinity would be negative in sign, right? And so all of that is captured there as well, okay? So let us go now to calculate the lattice energy of PBF2. Earlier, we had said that a formula that we could use was that delta H lat, right? So our lattice enthalpy, delta H lat would be equal to the delta H of formation minus delta HI, which was what represented our several steps, right? So the in-between steps, so several steps from our cycle that we did, okay? And those several steps are all of these guys. So all of these steps up until this point are what we're going to incorporate in our several steps. Okay, so let's start filling it out. Delta H lat is going to be equal to delta H of formation, which from the table that tells us that that is negative. It's here, right? Negative 664. So we're just going to drop that there. And then we're going to subtract from that the sum of all of these several steps, okay? So the several steps start here with the atomization of the lead. And if we look in the table, the enthalpy of atomization of lead is 195.52, 195.20 rather. So we're going to put that here, 195.20. The next thing that we're going to add to that is what? The 2 times the enthalpy of atomization of F2. So it's going to be 2 times this 79 here. So we're going to do 2 times 79. And then to that, we're going to add what? The enthalpy of first ionization of lead, which from the table is 716. So we're going to add that here. And then we're going to add the enthalpy of the second ionization of PB, which is 1450. So we're going to just add that here. And then after the second ionization, we're going to come over here. Now we're going to add 2 times, right, the electron affinity of fluorine. So it's going to be plus 2 times the electron affinity of fluorine, which is minus 328.16. Okay? So when we put all of this together, what we're going to come out with is a lattice energy of minus 2526.88, and that's going to be in kilojoule per mole, right? And so this is what we're looking for our delta H lat theta. So we can just box that as our final answer. We're just going to box that in red, okay? So this is our answer that we're looking for here, that our delta H lat is equal to negative 2526.88 kilojoules per mole. Okay? So that's what we needed to do here. All right. So moving right along, let us move on to the next question, which says, state the effect of each of the following on the magnitude, right, of lattice energy. So the magnitude of the lattice energy. So the magnitude just means like how big, right, or how large, rather, or how small the lattice energy will be. So that's really what they're asking us. How do these two things affect it? And so what we have to remember or orient ourselves with, first of all, is that the lattice energy, right? The lattice energy, it comes from the electrostatic forces of attraction. So it comes from electrostatic forces of attraction, forces of attraction between, I'm just going to write between oppositely charged ions. Okay? Oppositely charged ions. Because if you remember, right, what we showed for the formation of PbF2 was what we showed ultimately was that what we would be putting together would be the Pb2 plus in the gas phase, right? Plus the 2 moles of F minus ions in the gas phase. So when we think about lattice energy, we have to just always remember that the lattice energy comes from electrostatic forces of attraction between oppositely charged ions. And in this case, our oppositely charged ions are the Pb2 plus and the 2F minus, okay? So this is minus, this is positive. Them being held together, that's what constitutes the lattice energy, okay? And so when we think about ionic charge then, right, what we see is that the larger the ionic charge, so the larger the charge on the lead ion, that will give rise to a larger magnitude or a higher lattice energy, okay? Because if it's the charges that's driving the lattice energy, the forces of attraction between the charges, if that's driving it, the bigger the charge, the bigger the lattice energy is going to be, okay? And so we can say that concisely here as saying that ions with a high charge are attracted more strongly to ions of the opposite charge than ions with a low charge. And so they'll have a larger magnitude of lattice energy. Okay? High charge, lattice energy higher, right? So then finally, we talk about ionic radius. That's just the size of the ion. So how big or how small is the ion, and how does this affect lattice energy? Well, it turns out that if we have small ions, right, you can imagine that the charge is more condensed, right, or more densely populated on that small ion. So let's just draw a picture to orient ourselves. If we have a small ion like that, then we have a big old ion like this, from a radius standpoint, from an ionic radius standpoint, this one is larger, so the charge is more spread out, right? In this instant, the charges on it are more spread out, right? Than in the case where you have a teeny tiny ion with a small radius, small ionic radius, and so you have a higher charge density. And so if you have a higher charge density, then they're going to be more attracted to the ions of the opposite charge than in the case for large ions. And so small ions are going to correspond to there being a larger magnitude of lattice energy because they will be more tightly held. There'll be greater forces of attraction simply because the small ions have a higher density of charge on them. Okay? And so with that, we've come to the end of this question on energetics, Hess's law and the Born-Haber cycle specifically. And so definitely go ahead, give this video a like, comment down below to tell us if this was very helpful for you, and definitely consider subscribing and hitting the notification bell so that you'll be the first to know when we upload new content. Thank you, and see you in our next video.